Hi everyone, Dr. J here, and in this video I'm going to introduce you to the topic of inverse theory or inverse methods or inverse problems. Now this is a big topic and a whole semester course should be taught on it, but I'm just going to give you a little bit of kind of the concepts that go into this area, because really inverse theory is what all of geophysical data processing is based on. So whether it's seismic data, MASW, ERT, EM, everything that we do in geophysics is based on inverse modeling or inverse theory. And the reason for that is simple. What do we have when we do a geophysical survey? We have observations, usually at the surface, of some geophysical parameter. Electrical voltage in an ERT survey, responses from the electromagnetic responses in an EM survey. We have little vibrations of a seismometer or a geophone for a seismic survey. So we have these very, what you might think of as useless measurements without this technique called inverse methods, just vibrations or voltage differences or whatever, depending on the geophysical technique. And then somehow we have to go from those to our geophysical parameters of interest. For example, seismic wave velocities in the subsurface, resistivities in the subsurface. In the case of gravity, we're looking at densities in the subsurface. So how do we do this? How do we go from observations of something at the surface? In the case of gravity, that's going to be acceleration, local acceleration, tiny variations in acceleration that are due to density anomalies. How do we go from those observations, which seem very unrelated to the things that we really want, to those quantities that we actually do want? And we do this with inverse theory. So what I'm going to do is just give you a high-level overview of how this kind of works in practice, talk to you about some of the background and the mathematics behind that, and leave it at that for this class. So let's say that we're taking a gravity survey, and so there's the ground, we're walking along the ground, and we're taking measurements every so often. These little upside-down triangles just represent the station locations for, let's say, a gravity survey. And let's say that we take our measurements and we plot them up, and we get something which looks like this. And what I'll do here is I'll just draw points instead of drawing a line, because that's what we actually measure. So I've kind of tried to draw the dots above each one of their respective stations. Put out some gravity stations, we take some measurements, we get these measurements in the red. And these measurements are, I'm going to point out, it's important to realize that these are relative to a base station. So in regards to gravity, we don't usually get absolute gravity, we're getting gravity relative to a base station. So actually one of these points, and it depends on where our base station is, let's say that this is our base station, that point is going to be 0. So on our axis here, we've got x distance, and then y, this is going to be our gravity anomaly in milligauss. And our base station is here at 0 on the y-axis. Okay, so these are our observations. It's measurements of acceleration relative to a base station. What can we do with these measurements? Well, we know that gravity is related to mass. So more mass equals more gravity, higher acceleration. We also know that, gravity has a particular form, an equation, actually, that it obeys. And in our case, that equation looks something like, let's say, acceleration due to gravitational acceleration is equal to, we derived this in one of the other videos, capital G. In the normal case, we think about the mass of the Earth divided by the square of the Earth's radius, right? So this is the equation that we had derived before. Now, this gives us the total absolute gravity. But because we already are measuring the base station, we already kind of have this part accounted for, we're really only concerned about anomalies, about density anomalies, differences from the average, and in particular, differences from the base station average. So what we're going to do is we're going to modify this equation a little bit. And we're going to say that local g, let's call it delta g for the gravity perturbation, the gravity anomaly, is equal to, again, gravitational constant, little r, and r is the distance from the anomaly to the observation, so just write it as little r, and then that should be r squared, and then we have our mass anomaly, so we'll say delta m. And this is an approximation, so delta g is equal to delta m, and then we have our r squared and our g there. Okay. All right, so now what we can do is we can build a model. We can build a model of the Earth in this local area and account for this physics that we know about, and then use that physics in this model to try to solve for what this gravity anomaly is resulting from. Here's our grid, and so this is forming the basis now for our model. So we can imagine building a grid for the Earth's subsurface right underneath our survey line, and each one of those little grids is going to have a center point. I guess I'll use the same color. I'm not going to go through and mark them all, but you can see what I'm doing. At the center of each little grid, we have the center point of that grid. And now what we can do is we can model a point mass at each grid, and that point mass is actually a point mass anomaly, so a little delta m. So there's a little delta m here, and a little delta m here, and a little delta m here. Every single point in this grid has a little mass anomaly associated with it. And you can see, for example, these 2 points over here, the anomaly is 0 because, well, this is our base station. And so the delta m's over on this side of the grid are going to be likely to be equal to 0. So delta m is equal to 0. Delta m is, maybe almost equal to 0. And then there's some type of an anomaly as we go along the survey. And this anomaly kind of flattens out. So we kind of have one set of values over here, a different set of values over here, and then some transition. So over here on this side, delta m is some constant, some number. And I don't know what that is. I'll just call it n for number. But the point is, each one of these little grid cells over here probably have a similar number, n, because of the fact that there's no variations there. Either way, every single grid cell has an anomaly, a little mass anomaly, and that anomaly is related to the changes in acceleration. And since we're measuring acceleration going up, gravity is getting higher, local gravity is getting higher, this mass anomaly is probably positive. So there's more mass over on this side than there is on this side. Okay, so this is kind of conceptually how we'll do this. How does this work in reality, in mathematical terms? Okay, so again, we have our stations, we have our grid points, our survey points, sorry, and we're going to basically convert our model of the Earth's subsurface into a mathematical model. And we're going to do that using the physics equation that we had before. And so what we'll do is, for a given point, I'll just take one point here in the subsurface. The response, we call the impulse response, at a particular observation point related to a point mass anomaly at this location here. Let's call this x1, and that's a vector, so there's an x and y coordinate associated with that. We'll call this x2, again a vector, an x and y value associated with that. We're going to take the distance, this distance r, that's our little r in our equation. And actually, let me write down that equation again. So we have delta g is approximately capital G, gravitational constant, times delta m divided by r squared. So we have our r value now, and we have this little mass anomaly, that's what we want to find. We have this g, that's just a constant, and we can then, so basically if we know what the mass anomaly is here at this point, we can work out what the gravitational anomaly would be at this observation location. Do you see how that works? So if we know delta M here, and we know the position of this point, we know the position of that point, we can compute the distance between those 2 points. That goes in here. The mass anomaly goes in here. And then G is just a constant. And that gives us our gravity anomaly. So now I'm going to rewrite this expression a little bit. Delta G is approximately capital G over R squared. And then because we want to, typically we're interested in density. So we have mass anomaly, mass is related to the volume. So let's separate out those two things, volume and density. And we'll call this a little, let's call it V for volume. And then there's a density. So V delta rho, that's equal to mass. Volume times density equals mass. And so what we can do is we can actually rewrite this equation a little bit differently. And I'm going to do it in a different color. G times V over R squared in the parentheses, and then delta rho outside. So you see all I did was kind of rearrange the parentheses. G, gravitational constant, times V, volume of our little unit cells that we had around this point mass, divided by the square of the distance between the point and the observation point, and then we multiply that by the density anomaly. And then you can see, we're directly relating the gravity anomaly to the density anomaly. And so now this is how we're doing this for the gravity system, or for gravity surveying. This is how we're getting a parameter of interest, density anomaly, out of an observation, an acceleration anomaly. So we measure the acceleration at the surface, and then we use physics to relate that to density anomaly in the subsurface. Now we don't just have one point though. We have a whole grid that I showed before, really a whole continuum of points. And so what we often do in geophysics is to discretize the continuum into a bunch of grid cells like I showed you, and then solve for the density anomaly in each one of those little grid cells. Now, of course, as you can imagine, there are probably many, can be hundreds, even thousands of little grid cells, so these problems can get a little bit computationally interesting. But thanks to modern day computing, we can usually solve these kinds of problems okay. So what we're going to do is we'll pull out this term in parentheses, and we'll put it into a matrix. And unfortunately, I'm going to call that matrix G, because that's standard nomenclature. This is not the gravitational constant G, it's a matrix G. And the way that this works is we're going to say that D is data, is equal to G, capital G, and G stands for Green's function matrix, times M. And M stands for model. And in this case, actually, model parameters. So this here is our Earth model. G times M represents our grid of mass anomalies that we had drawn in here before. G is the part that we kind of put in those parentheses. So G is a matrix. A matrix has rows and columns. So if we take the ith row and the jth column, we'll call that little g ij, ith row and jth column of G. Okay, so we have little g ij, that's just the ith row and the jth column of the matrix G. G has rows and columns, and so we're going to take the ith row and the jth column, that's one unit in that matrix, one cell in that matrix, and that's going to be equal to the gravitational constant G, which I'm writing in blue here to try to distinguish between the big matrix G and the gravitational constant G. I have the volume of the jth element. So here is xj, we'll say. That's the jth element in our Earth model. So it's the volume of that element. And then the distance between xi, the distance between the xith observation and the xjth model position. So we have a model position, we have our observation position, we difference those two, well, we take the distance between those two, that distance comes in here, the volume of that element goes in there, and then we have the gravitational constant. And that is for one element in this matrix. And then what we do is we do this for every single element which is in our Earth model. So you remember that grid that I had? Every single one of those cells is going to get a value which is equal to this. And not only that, but every single one of those cells is going to get a value for each one of the observation locations. So every one of our stations is going to have a value associated with it that's different from every other station. So we have to compute the distance between every grid cell and every observation. That's why it's a matrix. It's a matrix which has the same number of rows as you have data, and then the same number of columns as you have model parameters, grid cells. Okay? And the only thing that we're missing here is the density anomaly. So remember we said that this has to be multiplied by the density anomaly to get the gravity anomaly. And so that's what goes into M. So M is a vector of gravity anomalies which are associated with each cell in the Earth model. So we take G times M, that's this term times the density anomaly, that's our physical model for how gravity works. And then that gives us the acceleration anomaly at each point, at each observation location. And so this is how we're building up this system of linear equations, or a matrix equation. D is a vector of observations, G is this matrix, and then M is the model parameters, the density anomalies in this case, which go with that matrix. Now, if this were resistivity, there would be a different model, but the concept would be the same. We're solving this linear system for the resistivity values in the subsurface in that case. Sometimes we can have nonlinear models, and in that case, there would be G would be a function of M. So M would go into some nonlinear function, and we would have to compute what the observations would be in that case. I'm not going to go into the nonlinear system, but in most cases, we're just using linear models anyway, where it's just G times M instead of G as a function of M. So if we know what the model parameters are, if we know what the density contrast is in the case of gravity, and we know what the Green's function matrix is based on the physics, then we can compute what the observation should be. But of course, that's not what we have. We have the observations, we have D. And if we know what the physics are, which we do in the case of gravity, we have G. We can compute, these terms for every cell. We can discretize up the volume, get the volume of each little element, we can compute the distance between each element and the surface, and then we have, of course, the gravitational constant. But we don't know what the density anomaly is. We know this stuff, we don't know what the density anomaly is, and that's why we separate it out, put it in its own vector, and call it M. That's the model. And so now what we want to do is solve for the model given a set of observations. And so this is called inversion. And this is why the whole field is called inverse theory. Normally you would have the model, multiply by the physics Green's function matrix, and get the data. In our case, because we're doing geophysical surveying, we have the data, we know and have an idea about the model, how the model works, how the Earth works, and then we're trying to use that to infer model parameters, density anomalies, seismic velocities, resistivities, and in our case, density anomalies. So we need to rewrite this system of equations. D equals Gm, that's our basic equation, but we need to put G on the other side because we want to get M by itself. Normally, if this were just numbers, you would just divide, right? So G is just a scalar, M is a scalar, D is a scalar, you just divide. Right? D over G equals M. That would be the case if they were numbers. But they're not. They're matrices and vectors. So a single line over the top means a vector, a double line on the bottom means a matrix. So we have to do something called the matrix inverse. G inverse is equal to the matrix inverse. And this is where we're getting into a little bit of detail about inverse theory. I'm going to kind of skim over that. Basically, we can't take the matrix inverse exactly because usually we don't have as many data as we have model parameters. In other words, we might have a gravity survey with 50 measurements. But there might be 1,000 unknowns in our model. And in fact, that's exactly what you're going to do for the lab, is you'll have 50 observations and you'll have 10,000 model parameters. So what we need to do is we have to manipulate the inverse of the matrix a little bit. And what we do is, let's see, G transpose G inverse, G transpose, and this is going to equal, this whole thing is going to equal what's called the generalized inverse. And I think the terminology is this G negative T. Again, this is a detail, you don't need to worry about it too much. Just know that there's some calculations that are involved in computing this matrix inverse. But once we get it, then we just have n, and now I'm going to use a hat for estimated. Estimated model is equal to this generalized inverse matrix times d. And so now you can see what we've done is we've done the equivalent of dividing through by g, we've multiplied through by the inverse, and then, so this is all fine except for one problem, which is that we still have less observations than we have model parameters. It would be like trying to fit a line through only one point. There's an infinite number of models that will fit, an infinite number of lines that will go through one point, depending on what the orientation is. And so we have to somehow, typically what we will do is somehow try to what's called regularize the solution. We'll smooth, we'll damp, we'll do all sorts of things to minimize the number of solutions that we can look at. And that'll give us a unique solution that we can actually plot up and visualize. Now the problem is that that solution is not unique and we can't overinterpret that solution. So you've all seen nice pictures of either gravity or magnetic or seismic inversions. And the question is, well, how realistic are those? How much can we trust what those results are? And that's where multiple geophysical surveys comes in. If you can do multiple surveys and get similar results from both surveys, you have more confidence in your results that your inversion is not introducing some artifacts from your regularization. And again, regularization is like smoothing or damping or something like that. We're trying to limit the oscillations in the model. We're trying to limit the solutions that we're willing to consider as being realistic. Okay, so that's about all I'm going to say, and what we'll do next is jump into the coding. I'll give you a little example of how to do the lab and run the inverse model. We'll build a forward model first, and then run the inverse model. And that reminds me, one thing I didn't say was we call this problem, we call this top line the forward problem, and this bottom line is the inverse problem. So the forward problem, we know the model parameters. We go forward through the operator to the data. And in this case, we have to invert the operator, this Green's function matrix, to go from the data back to the model parameters. Now you can see if you just look at this, that if we do some substitution here, if we say, okay, so let's say m hat is equal to this G, this funny inverse G matrix, and then D. Well, D is equal to the physical model times the true model parameters, so we can plug that in here. And now if you look at this, our estimated model is equal to the true model times this G inverse G. And remember we said this G inverse G should cancel out, and if the model or this inverse were a perfect representation of the true Earth, then that would happen. That would cancel out perfectly and we would get the estimated model as the true model. But what often happens, because again we don't often have very many observations, our observations are almost always either at the surface or very near the surface, it turns out that this quantity, this G inverse G, is often not exactly 1. It's often close to 1, but not exactly. And in fact, resolution is something you may have heard about. Resolutions, how things are resolved or not resolved as you go down deep into the subsurface. That's related to how close this quantity here is to 1. So it's related essentially to how well our model, our discretized model setup, relates to the true Earth. Or I should say, and it relates to how well our discretized model setup, or how well our data are sensitive to our discretized model setup. Okay, so that's a lot about inverse theory. I wanted to give that to you guys because it's used so much in geophysical software development and so forth. You will use it anytime you process data, geophysical data, but you will do, in the lab, you'll do an example where you actually create the forward model first and then solve the inverse problem. And we'll just do a very simple case where we don't really impose any regularization, and you'll see that the model that you estimate is very different from the model that's the true model. Okay, so we'll go over to the computer and see how that works.